For Computer Science 434, Artificial Intelligence, during the fall 2020 semester, we, Team 1, completed a project on an UNO AI. The team consisted of myself, Stefen Sharkey, along with Adam Czyryca and Michael Kowulich. During this presentation, we will be going over various aspects of the project, including other introductory information, contributions that this project serves to society, methods we use during all phases of development, the results of these methods, shortcomings, and next steps that we would like to have taken, and some project management information. We will be finishing by showing a live demonstration of the product we created.
For our project, we chose to create an AI that can play the card game UNO. We accomplished this through image classification and traditional AI. So our project uses a webcam to take a picture of an UNO card, which is then identified through image classification via Keras APIs. With the card determined, game logic is then performed using traditional AI methods. We chose UNO over other adversarial type games for two reasons. The first being that it is a card game, which made image classification easier, as opposed to something, say, a board game. And the second is the simple rules of the game that made the AI easier to train. Being new to AI, we felt that such simplicity was the best approach. For those who don't know, the game UNO is comprised of cards that have a symbol and a color, such as the example shown with the yellow 5. The game is then played by matching the color or the symbol of a card in your hand with the card on the top of the play pile, with the first person to empty their hand being the winner. So to achieve this, we use traditional AI for the game logic, that is, when and what card to play, and image classification to recognize what card the camera is detecting. As a result, we have an AI that can accurately identify the cards played by a human and respond appropriately as if playing against another human. The motivation behind this project's development was to further our knowledge of AI, being that we had little to no prior experience with its development. As such, we chose to base our project on an adversarial game since this gives us a practical example of how an AI can be implemented in the real world, as is demonstrated by the prevalence for which we see AI in the gaming industry. Our implementation of AI with the UNO game will never see market, especially since we cannot compete with large companies such as Microsoft, who already have a digital copy of UNO for sale. But the people who do have access to our project no longer need other people to play a game of UNO. They can play against any number of AI opponents, whether it be 1 or 100. The second contribution is a trained model of UNO cards. Since UNO cards are different from a regular deck of playing cards, during our research we were unable to find a pre-trained model of specifically UNO cards. However, one now exists.
Data collection was the simplest phase of the project, as the goal was simple: take pictures of UNO cards. Initially, this was discovered to be a tedious task, as the tutorial we followed had us manually labeling each card in every image we took. Eventually, we discovered a simpler method for us to follow, which simplified the data collection phase, but required us to discard all previous images taken. For us to maximize simplicity, we used the UNO Minimalista deck, which can be seen in this slide, as the cards on the deck only had essential elements added to the card faces. To maximize usability and accuracy of the models, we took pictures with different angles, distances, background complexities, background colors, luminosity, lighting colors, and cameras. The data aggregation methods we used changed multiple times throughout the course of the project. As stated, during the data collection phase, we were using a different technique than what we switched to at the end. The first data aggregation method we used was keeping every image in the same directory and using an image annotation program to create rectangles that indicated where the cards existed in the image and what kind they were. This turned out to be a daunting, tedious process. Eventually, we discovered a simpler method that allowed for us to take pictures of cards and place them in folders that were titled as the label corresponding to that image. For example, all yellow 7 cards would be placed in a yellow 7 folder. This would later be split into two separate models, separating the color from the value and classifying them separately. Now, in the color model, there exists blue, red, green, yellow, black, and blank labels. The value model contains all values from 0 through 9, skip, reverse, draw, back, wild, and blank labels. In both models, the blank label indicates that there is no card present in the picture. Data preprocessing also changed several times throughout the course of the project. In our earlier attempts, when we had one model to predict both color and value, we did not augment our data. However, later we found that data augmentation did improve our model's prediction of cards in previously unseen images. After separating our original model into two separate models, one for color and one for value, data augmentation proved to be effective at increasing accuracy even further. All images used for training and processing were scaled down to 299 pixels wide and 299 pixels tall to avoid lengthy training and prediction times. When training and using the value model, each image is converted to grayscale to make color an insignificant factor.
Our model training methods go for an image classification approach rather than an object detection approach. Originally, we attempted real-time object detection. However, the limited computer hardware that we all had made this infeasible with as many classifiers as we started with. Instead of pursuing object detection, where several parts of every frame are passed to the model for prediction, we investigated image classification, where the model observes the entire image at once and predicts based on what the entire image contains. This was much less costly on our hardware. We used Google Collaborate to train the model, as it allowed us to use their hardware that was much better suited towards training our image classification models than our own personal computers. We trained our model from scratch using TensorFlow's image classification tutorial, which used the Keras API with some changes to its data augmentation and model layers.
For the color model, we achieved what we felt was a reasonable accuracy and loss, as it had achieved an accuracy of 98.56% and had a loss of 0.0512. For the value model, we achieved less ideal accuracy and loss statistics, as it had achieved an accuracy of 95.54% and had a loss of 0.1300.
Some of our project shortcomings include the fact that our model has a difficult time predicting the color yellow in certain lighting conditions. Our model will also recognize 1s and 7s as each other, as well as 0s and skips. This is because these symbols are very similar in the way they look, and if we were to build a larger dataset, this margin of error would likely get smaller. As stated earlier, our model likes pictures that have a lot of white light in them, and does not work well with pictures taken in darker environments. Finally, most of the image must contain the card. Because we are using image classification in order to train the classifier, the majority of the image is supposed to be a card, and it expects the same thing when predicting a new card. Some next steps we would add for this project include a fully featured graphical user interface that would be more user-friendly. Another thing that we considered is that we recognize not everyone has the Uno Minimalista deck, so we would expand our dataset to include more popular Uno decks. Finally, the version of Uno that we set our AI to play is not the only version of Uno that exists. There are some that contain cards such as the Swap Hands card, where a player swaps hands with an opponent. Our project is something all members collaboratively worked on together. However, throughout the project, we have all taken on many roles. Stefen was the project lead and the lead developer. He delegated tasks to everybody and had weekly project goals for us to reach by the end of the week, as well as leading the development process. Adam and myself assisted in the development of the project as well as testing and gathering a large enough dataset to make our image classification more accurate.
My contributions to the project were mostly administrative, architectural, and programmatic. I determined how we would set up our model structure and how to categorize the image labels. I also modified the data augmentation and model layer code that was available on TensorFlow's website for image classification. And finally, I wrote a large portion of the Python codebase and rewrote initial code that Mike and Adam had wrote to make it more extensible to later additions and modifications we had made.
My contributions to the project include co-writing the initial logic of Uno and our traditional AI codebase, along with the collection and labeling of data to increase the dataset, rising the overall accuracy of the image classification. Additionally, I conducted tests to ensure the project worked as intended with the given parameters.
My contributions to the project include co-writing the initial game logic of Uno and our traditional AI codebase. I also researched image classification and object detection to figure out which method would be best for our project. One of the avenues I took to find out which method was better for our project was consulting online professionals on forums revolving around artificial intelligence and deep learning. Through all of those methods, I was able to pin down why our initial classifier was not working well at all, and this was because it was passed through a model that was not trained on anything close to our dataset.
Overall, this project was a success. The game logic with AI decision-making and object identification had all been implemented successfully. That is, the AI allows for the user to play against a non-human opponent, and the program can successfully identify an object of its trained model through a camera. Here you will see two major references of ours, an image classification and a data augmentation tutorial, both by TensorFlow. They both feature code snippets that we used heavily in our project. And finally, our appendix. We have our GitHub and our original source code. We do not have a dataset source as we trained the new model without any existing data. On to the demonstration now. On this window, you see that you can input a custom number of human and CPU players. Before the game is ready to take any input from the user will see the webcam feed on their screen. It will shortly after prompt them to select a card to draw. Here you can see the user is trying to draw a red 6. The image will then get processed by two different image classification models, which in this case predicted correctly as a red 6. I was unable to find a card that the model did not predict correctly, so what I did was I removed the card from the image, took the image, and then showed what it might look like if the card was predicted incorrectly. And you can see that there is an option for the user to correct the card prediction in case it is incorrect. Here you can see what it would look like when the game is requesting the user to play a card. As previously stated, the AI will know what kinds of cards can be played, and in this case it played a wild card, which can be played on top of any other card. In this case it also selected the color to switch to would be yellow. Due to the length of the average Uno game, a truly live demonstration would not be feasible, as it would well exceed the time limit for this presentation. For now, this concludes our project.